stopped it. Damn it. Okay, that's okay. It will be 2 recordings now. All right, so did anyone figure out what the inverse was? Like what is, for example, let's do maybe something concrete and then you could write it down. For example, if I give you something like, let's do 17265. So 17 inverse is equal to what? M minus 1. Okay, so Kenneth, I think you have like the right idea there. So in this case, if we had 17265, what would the inverse be? Like if I wanted to write it down, 56271. Okay, does everyone agree? Right, and because Justin, exactly what we identify is basically you just wrote it backwards, right? Because if the thing on the left sends take the element on the left to the element on the right, the inverse should just take the element on the right to the element on the left. And what is that? Well, you write it down backwards, right? So exactly. So again, another great benefit of cycle notation is it becomes very easy to compute the inverses. And then again, with disjoint cycles, you would just invert each of the disjoint cycles, right? So above, again, we have this, this element in S8, 17265, and then the cycle 48, and all like 48 is its own inverse. So there's nothing kind of crazy going on there. But this allows you to very easily and very quickly compute the inverse of a cycle. Not that it was too hard to do anyway, like in the case where, we use the notation, like this notation, right? The 1 to 7, 2 to 6, 3 to 3. It wasn't that bad because again, in that case, you would just kind of reverse the numbers as well. So that wasn't terrible, but again, another sort of benefit of cycle notation here. Okay. All right. So next thing we want to do is define the following. So definition, a transposition is just a 2 cycle. That's what a transposition is. Okay, so a 2 cycle is called a transposition. And again, if you think about what transposition actually means, and of course we've seen the word transpose before, like when we're talking about matrices, it's basically, again, just a switch, right? Just to flip things around. So transposition says, so for example, above 4,8 is a transposition. Is a transposition in S8, right? It's just going to flip the numbers 4 and 8. It doesn't do anything more complicated than that. It just kind of flips them around. And certainly every transposition is its own inverse as well, right? Every transposition has order 2 precisely because it is a 2 cycle. And we know that the order of a cycle, an M cycle, is M, right? So that is what a transposition is. And you might say, well, like, why do we care about transpositions? Like, why do we give them a special name and we don't give 3 cycles a special name or something along these lines? So for what we're going to need here is the following 2 results. So theorem, the first, and this, you might all say, like, this seems silly, like, why do we care? And I'll explain in a second why we care. Every element of Sn can be written as a product of transpositions. Now, I did not say disjoint, right? I did not say a product of disjoint transpositions, just that it can be written as a product of transpositions. Okay, and the proof is explicit, right? We can actually construct it. Note, and it suffices, of course, just to show that an M cycle, any M cycle, can be written as a product of transpositions, because then everything is built up, right? We know that every element can be written as a disjoint product of M cycles. So if every M cycle can be written as a product of transpositions, so can every element, right? So note that the M cycle, oh, y is, note that a1 dot 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 through am. I always write this the wrong way the first time I do it. So this is a1 am, a1 am minus 1 dot 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 a1. Maybe let me zoom out a little bit. A3, a1, a2. Okay, and again, you might have to think about this for a little bit about why this works. It's a little bit tricky, but basically, if think about, okay, where does A1 map to? Well, it maps to A2, right? If we look at the furthest most thing on the right, it maps to A2, and then A2 does not appear anywhere else, right? This is the last place that A2 appears. So A1 maps to A2, great. Now, where does A2 map to? So in the thing on the furthest right, A2 maps to A1, and the one beside it, A1 maps to A3, but then A3 doesn't get mentioned anywhere else. So that means that A2 must map to A3, and so on and so forth, right? Where does A3 map to? Well, the first place that A3 is mentioned is in the second transposition from the right. It's going to map, so A3 maps to A1. The transposition right beside it sends A1 to A4, and then A4 isn't mentioned again. So A3 is going to map to A4, right? Generally, you keep getting things of this form. So just kind of as an aside, right, you keep getting things like this, A1, AK, A1, AK minus 1. And so if you look at this, AK minus 1 is going to map to A1, which then maps to AK. And then you're done because AK is not mentioned again anywhere to the left of A1, AK. And AK is never again mentioned. Right? So this actually, you might have to think about it, right? But this, does everyone see that this makes sense? You might have to write down a couple of them, like choose a cycle and actually write it down. I guess, what's the cycle we've been working on? 17265. If we want to do it like a little bit more strictly, we could just say 17265. Okay, so what is that going to be? That's going to be 1, 5, 1, 6, 1, 2, 1, 7, right? And actually go through the multiplication and convince yourself that, yeah, this works, right? 1 definitely maps to 7, and that 7's never mentioned again. So 1 maps to 7. What does 7 map to? 7 maps to 1, 1 then maps to 2, so 7 maps to 2, and so on and so forth. So actually write it down, go through the multiplication at least once. There almost isn't anything to do. Again, it's just kind of tracing your fingers over each of the transpositions, right? To convince yourself that things map where they're supposed to. But once you convince yourself that this works for an arbitrary M cycle, voila, you're done. They're definitely not disjoint, right? It's not a disjoint product of transpositions, but it doesn't matter because that's not what the theorem said, right? It just said, boom, it can be written as a product of transpositions. Okay, and that's the proof, right? It's just, I can write an M cycle like this. Every element of Sn can be written as a product of M cycles, so I'm finished. Okay. Now, the next theorem that we need, this one, again, is not terribly hard to prove, though you do have to prove something else before you do it. So theorem, if you can write an element of Sn as an even number, or let's say the parity of the number of transpositions used to write down an element of Sn is constant. So the parity of the number of transpositions used to express an element sigma of Sn is constant. Okay, so what I mean by this, you might be like, okay, what the hell does that mean? Like, how do I read that? You have to think through it. But what it says is, if I can write my element sigma in terms of transpositions and I get an even number of transpositions, then no matter how else I chose to write it as a product of transpositions, I'll always have to use an even number. Okay, if I can write it as an odd number of transpositions, then every expression of sigma as an element or as a product of transpositions must be odd. Okay, so maybe let me include that so that we can parse this. So that is, oh no, I usually use green for note. So that is if you can write sigma as an even, and I'll put odd in brackets here, right? Number of transpositions. Then every expression of sigma uses an even and in brackets odd number of transpositions. Okay. Again, the proof of this fact is not terrible. You basically use the fact that the identity element has constant parity. In particular, the identity element must always be written as an odd number of transpositions. And then you say, okay, suppose that I have suppose that I have two different ways of writing sigma as a product of transpositions. Then right now the identity, so multiply one representation by the inverse of the other, that becomes the identity element. And then you say, well, how many, what was the parity of these two things? Oh, they had to differ by exactly 2 at most, right? Or some multiple of 2, which means that their parity is the same. Again, that one's actually in the book. I don't want to go through it because it discusses, you have to kind of make this argument that the identity element is always an odd number of transpositions. I don't want to do that. You should try and convince yourself of that one, but that one is in the book, right? But all you have to remember is if I can write it as an odd number of transpositions, it's always odd, no matter how else I write it. If I write it as an even number of transpositions, it's always even, no matter how I write it. Okay, so does that make sense? Right, so in particular, we see up here, in the example above, and if you have a question, keep writing it. So for example, right, we had 17265, that was 1516, 1217. So it took me 4 transpositions, which is even. So if I can find some other way of writing this as a product of transpositions, and maybe it's not exactly like this, but some other way of writing this as a product of transpositions, it must always have an even number of transpositions in it, right? So always, always, always will have an even number. Maybe I can write it as 6 transpositions or 8 or something like that, but there will always be an even number, okay? And we can't get away from that. Same thing, if it had been an odd number of transpositions, then no matter how else I had written it, it would have been an odd number. So therefore, we'll talk about an even permutation. So a permutation is even if it uses an even number of permutations or transpositions, and it's an odd permutation if it uses an odd number of transpositions, right? Okay, but what redundant transposition? Okay, so this is interesting, Justin. So what redundant transposition would you add though? Let's say to 17265. Because note that whatever you do, whatever transposition that you add now, you have to cancel it back out, right? 1, 5, 1, 6, 1, 2, 1, 7, 5, 6, but that's not the same thing now, right? Like that redundant transposition has actually changed what the element is, right? That's not sigma anymore, right? So no matter what you did, in order to get rid of the redundant transposition that you added, you're going to have to undo it, right? And so when you undo it, so whatever you add, you have to undo, and that corresponds to exactly always a multiple of 2. Does that make sense? Right. Okay, perfect. Yeah, because the redundant transposition that you want to add is somehow the identity, but the identity, you can't just write the identity as a single transposition, right? Because the identity as a single transposition, that would be impossible because the transposition is going to move things around. So eventually it has to cancel out, and it therefore always requires an even number of things, right? Yeah, so sorry, the identity is always an even number of transpositions. Okay, so yeah, maybe just let me quickly say definition. So an even permutation is one that uses an even number of transpositions, right? So we say that sigma in Sn is even, and in brackets odd, if it takes an even number. Why is my pen not working? You can finish writing it while I fix my pen if you want. If it requires an even brackets odd number of transpositions to write out. And again, this is now well-defined, right? Remember we were talking about well-defined? This is a well-defined notion because of the theorem we just said, which says no matter how you write it, it's always either even or odd, right? It stays consistent. If it's even, it's always even. If it requires an even brackets odd number of transpositions. Okay, so if you hear me say even transposition, you'll know what that means, and if you hear me say odd transposition, you'll know what that means. But now here's a little thing that we have to be careful about. So note an M cycle is even if and only if M is odd, which is kind of annoying, right? That the cycle is even precisely if its length is odd. But we've seen that. There is an example on the page right now. That sigma that I defined up there, that 17265, that has length 5, right? It's a 5 cycle. But when I wrote it as a product of transpositions, I needed an even number of transpositions in order to write it down. So unfortunately, there is this kind of parity switch, right? And we have to be a little bit careful about that. Evenness does not refer to the length of its cycles. It always refers to the number of transpositions. And again, the proof of this fact is, again, just the fact that when I write this thing down as a number of transpositions, remember I said it's A1 through AM, A1 through AM minus 1, ... A1, A2, this is exactly M minus 1 transpositions, right? Because there is no, I paired A1 with every element in the M cycle except itself, right? So that's why there's M minus 1 transpositions, and that's what screws up the parity. So if you have an M cycle, that means that in turn, you have N minus 1 transpositions. So even cycle lengths correspond to odd permutations and vice versa, right? So does that make sense? Just it's a little bit of a caveat that you have to be aware of. And again, right, because I can do it, because this is a cycle decomposition, all of them must have the same number or the same parity of number of transpositions, right? So here is, again, if this is an even cycle on the left, even cycle length, it has an odd number of transpositions. Because I could write it as an odd number of transpositions, they all must be odd, right? So it suffices for me to just give one transposition decomposition in order to determine whether a cycle is even or odd. Everyone's okay? Does that make sense? Okay. All right. So, I guess that leads us to this definition. For each n, and I think we want n greater than 3 here, but it doesn't really matter. The alternating group on n letters, and the way that we write that is A sub n, is the subgroup, and we're going to have to prove that it's a subgroup, but it's the subgroup of S sub n consisting of even permutations. Okay. So the alternating group is the subgroup of even permutations. Now, there's a couple of things that we have to ask ourselves. One, is this actually a subgroup? Right? So immediate sort of questions. One, is an actually a subgroup? And you probably believe that it is because I said so, right? But we should convince ourselves. Is AN a subgroup? And two, are the odd permutations a subgroup, right? That's a natural thing I think to ask as well. Why are we talking about the even permutations? Is an odd permutation, are the collection of odd permutations also a subgroup? Okay. So to my mind, and of course you can prove that AN is a subgroup using any of the subgroup criteria that you want, right? We have the first subgroup criteria, which is if X and Y are in H, XY inverse is in H, right? We have that one. And then the other one is just to prove that it contains the identity and it's closed under multiplication. Any of them, both of them work out pretty easily. Actually, you know what? Maybe this question is easier to determine if we answer question 2 first. So someone, can you tell me, are the odd permutations a subgroup? And why or why not? Like if you had to provide some sort of heuristic behind why this was true, why are the odd permutations a subgroup? Why or why not? There's a really quick answer if you think about it. Really quick one. Nobody has an answer for that? What is the parity of the identity? It's the identity permutation an even or an odd permutation? Anyone? No one wants to hazard a guess? It's even, right? Choose a transposition. Like I can write the identity as 1, 2 times 1, 2, right? As the transposition 1, 2 times itself. It's certainly the empty transposition, right? It's a product of no transpositions, but if you want, choose any transposition you want or any number of transpositions. You need to, like, if I can write the identity as 1, 2 times 1, 2, that's an even number of permutations. And so it's an even permutation, right? Yeah, and 0 is also even, right? And that's exactly what I'm saying. If you wanted to write the identity as 0 transpositions, well, 0 is even, right? Exactly. So the identity is an even transposition, which immediately tells you that the product or that the odd permutations is not a subgroup because it simply doesn't contain the identity. But something else also goes wrong. If you take the product of 2 odd permutations, do you get an odd permutation or an even one? Anyone? Why is my pen not working? There it is. You can't think about it? Okay, so say you have sigma and tau, and this is odd because it requires 3 transpositions, and this one is odd because it requires 5 transpositions. How many transpositions does it take to now write sigma tau? Like if I chose to write them out like this, it takes 8, right? So it's even. So the product of two odd permutations is an even permutation. So the collection of odd permutations super fails to be a subgroup. It's not closed under scalar multiplication, and it doesn't contain the identity. It's definitely associative, but it fails those two things, right? So for number 2 here, the odd permutations don't contain the identity. And aren't closed under the binary operator. Right? So it super fails to be a group. Now, what you have to convince yourself is that the even permutations do satisfy all those properties. Definitely contains the identity, right? No problem. Multiplication is associative, and we get that one for free because multiplication is associative in Sn. So it's certainly associative in the subgroup. And yeah, the product of an even number of permutations with another even permutation is an even permutation. So yeah, it is a subgroup, right? Right, just thinking about it. Again, you can actually run through one of the subgroup criteria if you want, but again, it all comes down to this fact that the product of even permutations is even, because when you add two even numbers, you get an even number, right? It comes down to this fact, right? Even plus even is even. And that's the reason why it works. And that's also, you can see the reason why it doesn't work for the odd permutations, right? Because odd plus odd is even, not odd. Okay. So I guess we need maybe one more theorem. The order of an is exactly n factorial divided by 2, right? Again, let's say n is greater than or equal to 3 here implicitly. Okay, so there are exactly half as many, if you take a look at the order of the group, there are exactly half as many, or exactly half the elements are even, right? And the way that you do this is you just argue the number of odd permutations and the number of even permutations are exactly the same. And therefore, you know, they both must have the same number of elements. And so the number of elements that they each have is n factorial divided by 2, right? That's 100%. The proof is exactly that. Usually, if you want to make it a little bit formal, you say, look, an and bn, or sorry, the even permutations, the odd permutations are in bijection with one another, and you can explicitly construct that bijection. And then you just say, look, they're the same size, right? So the idea of the proof, so you can map, so if O(n) are the odd permutations, then this function is a bijection. Okay, it might take you a little bit to prove that it's a bijection. Actually, in this case, don't prove injectivity and surjectivity. If you want to convince yourself it's a bijection, construct the inverse, right? That's sort of what I think is probably the easiest way of doing it. But again, just convince yourself it's a bijection. So the number of even permutations is equal to the number of odd permutations. And of course, every element of the group is either even or odd. Sn is On plus An, which is 2an. So An is Sn divided by 2, which is n factorial divided by 2, like that. All right, that's basically the proof. Again, the only part here that requires a little bit of checking is that this is a bijection. It's evident that I hope that if I give you an even permutation, multiply it by another transposition, then it becomes odd, right? So certainly that this function is well defined. And then again, all you have to do is convince yourself that it is in fact a bijection, right? And then the rest of the proof is immediate. Okay, any questions? Now, a very reasonable question to ask is like, why do we care about the alternating subgroup? Is it just a nice example, or does it actually matter? Does it actually come up? And so the alternating group is responsible, frankly, for one of the most profound and one of the coolest theorems that we have in mathematics. Now, I could misquote basically how this works because it's been a while since I did Galois theory, but basically here's the deal of it. So you all know that there's a quadratic formula, right? And again, if we think about a quadratic formula, so here, let's just think of this as an aside. And if you take enough algebra, you'll eventually learn this. So as an aside, so we know if we want to find the roots for ax squared plus bx plus c equals 0, there's a formula for that, right? B squared minus 4ac all over 2a, right? This is the quadratic formula. Now there is a cubic formula. It's quite messy. It's quite long, but there is one. And there's also a quartic formula. So there are also cubic and quartic formulas. i.e., if you gave me an arbitrary cubic polynomial, ax cubed plus bx squared plus cx plus d, and you set that, you want to know what the roots of that is, there is an expression of that just involving addition, multiplication, division, and nth roots, right? So, or let's just say addition, multiplication, subtraction, division, and their nth roots. And there are formulas. Now, in practice, you would never, ever use those formulas. If you get an opportunity, just Google the Quartic Formula, and you will see that it is the worst thing in the world. That like I could not write it down on this because there's just not enough space on my like tablet here for me to actually write down the Quartic equation. In fact, if you want to do that right now, go into Google, ask it for the Quartic equation, and you will see that it is the worst thing in the world. Nonetheless, theoretically, it's an interesting question. Yeah, right? Yeah. So you looked it up and you're just like, no, who would ever use that? Especially when you have things like much better techniques for doing that, right? But nonetheless, the Quartic equation, yeah, it's nasty. In fact, maybe I will, the Quartic, or I guess the Quartic Formula is what it should be called. And I kind of want to share it on the screen just so for recording reasons it exists. But, oh man, what? It's surprisingly a pain in the butt to come up with. Ah, well, whatever, it's somewhere. Yeah, you can Google it. So it's a nightmare, right? So the natural question is, for a long time, people were asking, is there a Quintic formula, right? Is there a formula for the fifth order polynomial? And you can imagine it's already kind of messy to find cubic and quartic, and it seems to be getting way worse every time. But people were looking for a Quintic formula and couldn't find one, right? And again, a lot of hypotheses could be just that it's so nasty and it's so hard. And if you've ever seen the derivation of the Quartic formula, it's a nightmare. It is not easy. You can imagine, if you've seen it, you're like, how the hell would anyone even find this? So the derivation of the Quartic is complicated. Maybe the only reason why we can't find a Quintic is because it's so hard, right? And so same sort of things, the sectic and septic and octic equations or formulas, whatever the case might be, there's this question of, do any of them exist? And you can prove mathematically that there is no Quintic formula. There is no general expression, no matter how ugly, that involves only addition, multiplication, and the nth root function that will allow you to solve an arbitrary Quintic formula. Obviously, if the Quintic is very nice, there are things you can do, right? Like if it's x to the 5 minus 32 equals 0, I think you could solve that, right? But as a general rule, there is no Quintic formula. And how do you actually prove that? Where does the proof for the non-existence of the Quintic formula come from? Well, it turns out it comes from the alternating group. So the existence of a Quintic can be basically tied to this thing right here. And it turns out because of some property of A5, you can prove that there is no quintic formula. And this, you should be going like, how the hell is that even, what does the alternating group on 5 letters have anything to do with the existence of a quintic formula other than the fact that the number 5 appears in both cases? And you say like, yes, absolutely. But the real reason is that you can relate the existence of, so basically there is a quintic formula if and only if S5 is what's called solvable. And we won't talk about solvability in this case or in this class. You'll have to go take a course in Galois theory. But S5, the quintic formula exists if and only if S5 is solvable. And then if I recall correctly, a group is solvable if and only if every single one of its subgroups is also solvable. And you can prove that A5 is not solvable. It's hard to show that S5 directly is not solvable, but A5 is easy to show it's not solvable. So since A5 is not solvable, S5 is not solvable. And since S5 is not solvable, there's no quintic formula. And then this immediately implies that there's no formula for any polynomial of degree n greater than or equal to 5, because A5 naturally is a subgroup of S5, but it's also a subgroup of S6 and S7 and S8 and so on, right? These all naturally are subgroups of one another. And so the moment that A5 stops being solvable, it guarantees there are no formulas for anything greater than or equal to 5, right? And that's how you prove that there's no quintic formula or anything higher than that. So A5 ends up being really, really important for this reason, right? And of course, it's important for other reasons as well, but here's kind of like a really cool example that the math is fairly complicated for this, but shows you the importance of the alternating groups, right? They're not just something that we do because they're nice examples, but because they actually are mathematically very important. Okay, so that's just kind of a rundown of how these things work. I would suggest that you practice with these a little bit. Just mess around with some cycles, try and see if you can break them up. Practice taking arbitrary elements of the symmetric group and writing them as n cycles or as disjoint cycles, and then taking all of those cycles, writing them as transpositions, determining whether or not something is even or odd. Even better, and I think here's a really cool thing if any of you are interested in it. All of this stuff can be done with a computer, right? In theory, and it's kind of up to you how you want to implement it, but you could set it up so that I give you a function, which is an element of Sn, and you immediately compute its disjoint cycle decomposition, its product of transpositions, its parity, its inverse, all these things you could do in, say, Python, right? If you've taken 108 or 148, all of those things can be done in Python. So that's kind of a cool thing to do if you're interested. The other cool thing is, if you want to think about it, I think you've all seen Rubik's cubes, right? And if you think about it, the Rubik's cube, how many squares are on a Rubik's cube? So there's 9 to a face, and it has 6 sides. So that's 54 faces. Is that right? That sounds. There's 54 little squares on a Rubik's cube. Yeah. Okay. So think about every move of a Rubik's cube is just a permutation. Right? Like if you take, like, let's say you've got this Rubik's cube, this 3 by 3 by 3 cube, and you just kind of like, flip the top, that's a permutation, right? And then you flip the side, that's a different permutation. So the Rubik's cube forms a group. The collection of all possible permutations of the Rubik's cube is a group. Now it's not S54, right? It's a subgroup of S54, but can anyone tell me why the Rubik's cube is a strict subgroup of S54? How can I just conclude that immediately? Why is it not all of S54? No ideas? So let me put it like this. S54 is the collection of all possible permutations, right? Wouldn't S54 allow for a cube to have all one color? Not necessarily. So what you're going to do is you're going to say, listen, I've got these 54 elements, but I'm going to say that they're all a particular color, right? So I'm going to like number 1, 2, 3, 4, 5, ... all the way up to 54. But then I'm going to say that these, maybe the first 9 numbers are all red or something like that, right? And what I'm doing is I'm saying, look, of this red face, this is going to be like 1, 2, 3, 4, 5, 6, 7, 8, 9. So I know that they're all red, right? But then if I choose another face, maybe I'll number these 10, 11, 12, 13, 14, 15. Maybe this is the blue face. So I know that the numbers 10 through 18 are all blue, right? Exactly, Kenneth, exactly. Notice that the center square is always the center square, right? This thing right here, the center square, can never not be a center square, right? It can't suddenly go up here, right? It can't be a square in the top right-hand corner. The center square is always the center square. And the full S54 would 100% allow you to move a center square into any other square, right? You can move any square to any other square, but there are natural restrictions. You can't move the center square to something which isn't the center square. So it can't be all of S54. Nonetheless, the Rubik's Cube group is ginormous. Even if it's not all of S54, remember the size of S54 is 54 factorial, which is a stupidly big number, right? So even if the Rubik's Cube group is a small fraction of the size of that group, it's still gigantic, right? Think about all the possible permutations you can do with the Rubik's Cube. It is a gigantic, gigantic group, right? Nonetheless, it turns out you can do something fun and cool called non-commutative Gaussian elimination, the same sort of Gaussian elimination that you learned in linear algebra, right? Like when you row reduce a matrix, right? That's Gaussian elimination. You can do a form of row reduction on on the Rubik's Cube group in order to take an arbitrarily but legal configuration of a Rubik's Cube and figure out the steps that you would need to do in order to solve it, right? So when you row reduce a group to the identity, sometimes you want to keep track of the row operations that you did because these correspond to, for example, the elementary row operations. You would do the same thing. There's a way of taking the Rubik's Cube, writing it like a big old matrix, and reducing it to the identity. And you have to be careful. This isn't straightforward because things don't commute in S54 or in the Rubik's Cube group. But you keep track of the steps that you do, and then if you do those steps in reverse, you can actually solve the Rubik's Cube. So it's possible to program a computer to do this for you. So given any configuration of the Rubik's Cube, a computer can solve it precisely by this algorithm. Okay, so that's kind of like a cool thing that you can do. Again, the math of the Rubik's Cube is a little bit too advanced for us, just a little bit. It's not that hard, but it's a little bit too advanced. But these are examples of subgroups of the symmetric group as well, right? As a cool little thing. Okay, but we're basically out of time. It's certainly not enough for me to do anything else. So are there any questions about this material before we take off, before we end the lecture? I have office hours right after, of course, so we can continue, but. No, everyone's good. Okay, then as far as I'm concerned, our lecture is done. I'll see you all on Thursday. Don't forget that you have quiz 1 on Friday. So start preparing for that. And otherwise we'll just go into office hours.